So last time we had a little bit left over. We want to cover Bayes' rule. What is Bayes' rule about? Bayes' rule is about somehow taking a representation of a distribution, slicing it up, and getting out a different representation of that distribution. More mathematically phrased, typically, let's say you have two random variables, x and y. You can apply the product rule in two orderings, which gives you two different ways of writing out the joint between x and y using a conditional and a marginal. If you now divide both sides by p of y, you get this expression over here. And this particular expression is so useful that it's gotten a name of its own. This is Bayes' rule. This is a really helpful equation to know just as shown here, rather than having to rederive every time you want to use it. We'll use it a lot, and the beauty of this equation is that often it's easier somehow to come up with a model that works in one direction than in the other direction. For example, it might be easier to come up with a model for y given x than to come up with a model for x given y. And Bayes' rule then gives you a way to get the distribution for x given y after having built a model for y given x. Applications are manifold. They include things like automatic speech recognition and machine translation, where it's much easier to write down a word, then pronounce it, and build a model for from word to pronunciation than the other way around. And then you'll use Bayes' rule to flip that around to reason about once you heard something, what word was being said. This equation is used a lot everywhere in probabilistic reasoning, in machine learning, and so forth. So even though it's quite simple, it's one of the most important equations that we have right now in AI. Here's a typical example of how this works. You're often interested in finding out what the most likely cause is of some effect. But it's really hard, when you observe an effect, it's really hard to build a model that directly gives you this conditional over here. It's easier to, either through physics considerations or through experimentation, build a model of the type, given a cause, what is the distribution over possible effects? So you'll end up building that model, the effect given cause model. You'll build up a model for the a priori probabilities of each cause, and then this thing at the bottom here, something we know we don't have to worry about. That's just a normalization constant. We don't need to actually build a model for that. So let's look at an example. Disease diagnosis. There are two random variables, M for meningitis, S for stiff neck. Let's say you are given, because those are easier to obtain, the distribution for having a stiff neck given you have meningitis. You have the prior for somebody having meningitis and the prior for stiff neck. Then you can use Bayes' rule to flip this all around and get the distribution for what's the probability of somebody having meningitis given that they observe they have a stiff neck. Apply Bayes' rule, fill in the numbers, and here's the probability. So this is the way you use Bayes' rule in almost all cases. Tying it back to something we saw a lot earlier, utilities. Even though the posterior probability of meningitis is quite small, that doesn't mean you shouldn't go see a doctor if you have a stiff neck and you're concerned about meningitis, because the utility of undiagnosed meningitis is really, really bad, and the cost of going to a doctor might be pretty low. So it's not just the probability that it will affect your decision making, you will still have to consider the utilities and so forth to decide, even when the probability is low, it might be that you take some action. Yes? Oh, it's not all the way down. Look at that. That's interesting. I don't know if I can just pull that. Thank you. Okay, let's work together through a little quiz here. We have a prior for capital W, weather. We have a conditional for dry or not dry, given the weather, can we find a distribution that gives us the distribution over weather, given we observed the conditions are dry? Okay, Bayes' rule tells us this is equal to the probability of dry given weather times probability for weather divided by the probability for dry. Now, what do we have? This one over here we have. The prior we have. This one here we don't have. It's the prior for dry. We know it's just a normalization constant, so we might just ignore it for now. Or if you really want to find it, we know how to compute it directly. This is equal to the probability of dry given wet. No, not given wet. Dry given sun times probability of sun plus the probability of dry given rain times probability of rain. So at this point, for any value for weather, whether it's sun or rain, we can fill it into this equation here and find the number. So let's do probability for sun given dry. We have dry given sun, which is sitting over here, 0.9, times the prior for, this case, sun, which is 0.8, divided by the normalization constant z. We can do the same thing for rain given dry, which will be rain given dry over here, 0.3, prior for dry, 0.8, divided by normalization constant z. So we have 0.72 over z and 0.24 over z. We know z is just a sum of these two things, 0.72 plus 0.24. And so we have the final answer to our Bayes rule kind of problem here. Remember at the beginning of last lecture, we looked at Ghostbusters. And let's actually look at that demo. Here's the prior distribution for the location of the ghost. So we have a prior distribution for the location of the ghost. We have a model for how a sensor will work as a function of the location of the ghost. The color will vary as a function of how far you are away from the ghost. That's our ghost location is the cause, and the sensor is the effect. So we have our cause to effect model. But what we're interested in is, of course, the reverse. Given some measurements, where is the ghost going to be most likely, or in general, what's the distribution over locations of the ghost given a sensory reading? So when we make a sensory reading, let's say over here, what's happening underneath here is Bayes' rule is applied, and we compute the posterior of location of the ghost given this sensory reading, which was green in this particular square. Now we have a new distribution for location of the ghost. This is our new prior. We still have our sensory model. If we make an observation, maybe over here, we can apply Bayes' rule to incorporate that sensory reading and get a new posterior distribution, which is now the distribution for where the ghost might be, given both sensory readings. We can keep repeating this, and that's what's going on underneath. Every time we make a measurement, maybe now we'd go over here. There was a measurement model that models probabilistically the relationship between ghost location and measurement. That model we have. We use that in Bayes' rule to find the posterior over location of ghost given measurements. And every time we click on something here, underneath the code is applying Bayes' rule and updating these probabilities accordingly. Then maybe at some point we decide we've seen enough and we take an action. Okay, let's switch to Bayes nets. We've looked at the probability distributions. They're models of the world. In general, these models will be imperfect. The reason they'll be imperfect is because we don't know perfectly how the world works, or maybe we don't want to model everything about the world because a really detailed model is just maybe computationally too expensive to work with. In general, any model we build is going to be an approximation. What's really important, though, is even though all models are wrong, some of them will be useful. And so you want to kind of be at the spot where your model is still useful, even though it's not perfectly accurate. Useful both in terms of giving you some information about the world and at the same time being crude enough that you can still compute with it in a tractable way. What kind of models might we be interested in? We might want to do diagnostic reasoning, where you measure some effect and want to find out the cause of that effect. Prediction. You might want to predict ahead of time what will the weather be like over the next few days. Or you might want to compute what the value is of collecting certain amounts of information. What is the value of making an additional measurement in Ghostbusters? Is it worth it? Or should you just go ahead and already hit at the most likely square? The first property we're going to use a lot is independence. What's the idea here? Well, if you have a distribution over two variables, x and y, those variables x and y are considered independent if this property holds true. That is, for all values x and y can take on, the joint probability of x and y is equal to the probability of x times the probability of y. What that means is that this joint distribution actually factors into two separate distributions. These two separate distributions that are smaller together contain the same information as the joint distribution. Another way of writing this is as follows. The conditional of x given y is the same as just the marginal for x. This is saying that if you were to measure y, and you were to, let's say, apply Bayes' rule and get then the conditional for x given y, having measured y is giving you no information about x. The distribution is not changing. How can we go from the first one to the second one? We just fill in the definition of conditional probability, x comma y over y. Then we use this equation over here, equal to px times py over py. And now we cancel out py, and we get that indeed, if x and y are independent, which is this condition over here, then probability of x given y equals the probability for just x without any knowledge about y. We'll have a shorthand notation for this, which is x orthogonal to y. Are many random variables independent in practice? Not all that often are they independent. It can happen, though. Let's look at one of our running examples for this lecture here. Let's say you're interested in the random variables weather, traffic, cavity, and toothache. It might be reasonable to assume that weather and traffic are independent of cavity and toothache. You could argue against that. For any of the models we come up with, you could argue against the assumptions we make. That's always going to be true. And when you apply this in the real world, it'll be up to you to decide what's reasonable enough in terms of assumptions, and at the same time, keep your model simple enough. How do we verify independence? Let's say you are given a table, a joint distribution for T and W. How do you check if T and W are independent? Are they independent? Any hunches as to whether T and W are independent here? Well, it's hard to see from just looking at the table. You need to sometimes go back to the definition here and see if that definition is true or not. If you find a violation, then they're not independent. So how do we do that? You build the marginals, which we saw how to do last lecture. Then you build a new table, which is equal to the product of the marginals. For example, this 0.3 comes from multiplying this entry with this entry over here, probability of hot times probability of sun. And then we check, are these tables the same table or not? Well, already in the first entry, we see a difference, 0.4 on the left, 0.3 on the right. This means these tables are not the same, which means that we don't have it to be true that for all T and W, PTW equals PT times PW. And so T and W are not independent. What's an example of where independence might actually be true? Let's say you had a bunch of coins, you're going to flip them all, and going to measure whether they came out head or tail. These are independent flips. These coins are all independently set up. They're not stuck to each other and so forth. Then this would be independent random variables. You could have many of those coins. And what's really interesting here is that if you think of this, you have these many, many coins, let's say n. You have n tables, each of them having 2 entries. If you think about the joint distribution between all n coins, you want to set that up. That's a table with 2 to the n entries. So by realizing that there is conditional independence, you can model this set of random variables by just a set of n separate tables rather than one joint table and encode the same information. And that's really where the gain is going to be coming from, is making assumptions that allow us to not have to model the joint distribution as a full table, but somehow split things up into smaller parts that still encode the same information. Independence is, of course, a very strong assumption. If we always make the full independence assumption, we're not going to be able to model a whole lot of real-world phenomena, but it's an example here to show that if you make some assumptions, in this case independence, you can get a much smaller representation that encodes the same information as the full joint distribution. So the assumption we're going to make instead of independence is conditional independence. It's a more subtle assumption, and it'll be more readily applicable to real-world problems. Let's start with an example. Our 3 random variables are toothache, cavity, and catch. If I were to have a cavity, the probability that the probe catches in it doesn't depend on whether I have a toothache, because the probe is just interacting with the cavity, not with my feeling of pain or no pain. So probabilistically, what's happening here in our joint distribution is that it satisfies a property. This property over here, the probability of a catch, given there is toothache and there is cavity, is the same as the probability of catch, given that there's just cavity, and we don't know whether there is toothache or not. So once we know there's a cavity, whether there's a toothache or not doesn't give us any additional information about whether there's going to be a catch or not. That's conditional independence, where one variable makes another variable irrelevant to a third variable. The same holds true when there is no cavity. In that when there is no cavity, getting the additional information of having a toothache or not is not telling us anything about the probability of having a catch of the probe. If this is true for all instantiations of the random variables, that we can leave out the toothache occurrence over here, then we write it this way. We now, instead of values from the domain, have the actual random variables in this equation, saying here the random variable catch, random variable toothache, random variable cavity, and here toothache is left out. That's a shorthand notation for this being true for all instantiations of catch, toothache, and cavity. Question? Yes. Okay, so the informal statement that I gave is that if you have 3 random variables, and once you know the second variable, information about the third variable doesn't influence what you know about the first variable, you have conditional independence. So there's this mitigating variable sitting in the middle in some sense, that if you know that variable, the 2 other variables don't give any information about each other anymore. We'll give a more mathematical definition on the next slide. But that's the intuition. You can state this in many equivalent ways, what we just wrote up here. you can write this equation here, saying that conditioning on, we had here catch was independent of toothache. Now, given cavity. When that's true, we can also swap the roles. If you look at this equation here versus this equation here, we swap the roles of these two. These occupy symmetric positions really in this, what we're doing here. It's really the fact that cavity is making them independent. The cavity is making catch and toothache independent. So you can write it just as well this way. The probability of a toothache given catch and cavity is the same as the probability of toothache given just the knowledge that there is a cavity or not. And you can write this in a third way, which is as follows, saying that the joint distribution for toothache and catch given cavity is the same as just the marginal for just toothache given cavity times the marginal for just catch given cavity. This is very similar to what we had for independence, where we had x comma y equals x times y. Here we just condition on cavity everywhere. Other than that, we have the same equation. Okay. Why do we care about conditional independence? It's some structure in distributions that will allow us to encode them more compactly. Independence is just too strong of an assumption, even though that makes things really efficient to encode. It doesn't really allow you to approximate the real world in a reasonable way. The notation we use for conditional independence is this notation here. This is saying that x is independent of, conditionally independent of y given z. The definition is that this conditional independence of x and y given z is true if and only if for all x, y, and z, the joint over x and y conditioned on z is the same as the conditional of x given z times the conditional of y given z. So it's showing that once you know z, there's nothing you need to model about the interaction between x and y anymore. Equivalently, you can write it this way. And that's often the way we will be using it. For all x, y, and z, the conditional of x conditioned on both z and y is the same as the conditional for x conditioning just on z, showing that the additional information of y is not saying anything about x. Yes? Which equation are you referring to? Which equation are you referring to? The first one? Sure. Okay, good point. So the way the notation works is as follows. The conditioning bar can only appear once. So your question effectively was, is there something like px given z, comma y given z? Does that exist? That notation doesn't exist. You're always conditioning once, and that conditioning is valid for all the variables in that expression. Yes? Yes, so I think that's how I interpreted this question, but maybe the answer didn't reflect that. So when you write any set of variables here, consider these as one entity together, and then the conditioning bar separates that from whatever you condition on. And there could be many things conditioned on. You could have things like x1, x2, x3 conditioned on y1, y2, y3, y4. Then this is the conditional of the joint between x1, x2, and x3, conditioned on all four y variables having been observed. And so there's just one time of conditioning happening, and it's for all of them at once. Okay, let's look at conditional independence examples. We have 3 random variables here: traffic, umbrella, and raining. What conditional independence assumption might be reasonable for this domain that we're trying to model? Well, any suggestions? Yes. So the suggestion was umbrella conditionally independent of traffic given rain. Why would that make sense? Because rain, in some sense, is the common cause. Rain will determine whether there's going to be a lot of traffic or not, and rain is going to determine whether people are carrying umbrellas or not. And there is no direct relationship between carrying umbrellas and traffic that's not mitigated through the cause, which is rain. Another one: fire, smoke, alarm. What conditional independence might we have here? Over here. Fire independent of alarm given smoke. Why might that be a reasonable assumption? This is effectively encoding a relationship where fire might cause smoke, which might cause the alarm to go off. And the fire will not directly cause the alarm to go off, only mitigated through smoke. Hence, fire is independent of alarm given smoke. All right. The way we'll be using conditional independence to build smaller models, more compact models, is through starting from the chain rule. The chain rule was this thing where we had this product rule, where the joint over x and y could be written as a conditional of x given y times the marginal for y. And we could apply this repeatedly if we had many random variables. And that was the chain rule. Looks like this. You expand the joint over x1 through xn as marginal for x1, conditional x2 given x1, conditional x3 given x1 and x2, and so forth. If we apply this to the traffic, rain, umbrella domain, here's what we get. That's just applying the chain rule. This is always possible for any distribution over a set of random variables. No assumptions are being made. But now if we're willing to make an assumption, let's say the conditional independence assumption, then what we get is a simplification. We can simplify this last one here. If we assume that umbrella is independent of traffic given rain, we can make this simplification here. Why is that interesting? Well, this is a table over 3 random variables over here. This is a table over 2 random variables. So we shrunk the table that we have to use to represent this distribution from a table over 3 to a table over 2 variables. If we're willing to make more conditional independence assumptions, we'll be able to cut out more variables from tables and have more compact representations. Here's another example. Let's look at Ghostbusters in a very simple case. There's just 2 spots the ghost might be at. There's a sensor. So the random variable says G is whether the ghost is in the top drawer or not. There's a sensor, T. The top square is red or not red. And then there's another sensor for the bottom square, which could be red or not red. This is what's given when we modeled this particular scenario. We have a prior for where the ghost might be, 50-50. We have a sensory model that works as follows. The probability of measuring the ghost, measuring red on top, if the ghost is in the top drawer, is 80%. So 80% of the time we kind of measure the right thing there. If the ghost is up there, probability of measuring the ghost on top when the ghost is not there is 40%. So again, noisy, but in the right direction. And then same for the bottom drawer. So what do we have here? Effectively, we have a distribution for G. We have one for T given G, and one for B given G. 3 tables. If we apply the chain rule, naively, we would get something like this. This would be equal to, if we put G first, the distribution for G times T given G times B given T and G. But we assume that these sensors are independent given a fixed coast location. So we assume B is independent of T given G, and we can simplify from this thing over here to this thing over here. Again, we go from a table over 3 variables to a table over just 2 variables, which makes our representation more compact. From this, you can build back up the full joint distribution. That's always possible. But in principle, we could represent this a lot more compactly just with these numbers over here, thanks to this conditional independence assumption here that T and B are independent given G. Okay, let's start making this more formal and start building this into Bayes nets. Why Bayes nets? If you have a lot of random variables, the full joint distribution is too large to work with. You want a more compact way of representing it. They give us a technique to describe distributions more compactly and also a graphical notation that gives us a lot of insight into the structure of the distribution. The main idea is that we will be capturing local interactions between variables rather than one big global interaction. So let's kick it off with a real Bayes net example. Let's say you want to model a distribution over a bunch of random variables that relate to car insurance. This might be the Bayes net that you would come up with. And we don't know yet exactly what that means, but for now, what we're looking at here is a graph. In that graph, there are many random variables. And whenever there's a direct influence between random variables, we connect them. So we might say the socioeconomic status has a direct influence on whether somebody has an extra car or not. The socioeconomic status has a direct influence on the vehicle year of the car that somebody might be driving. Whether there is anti-theft devices installed has a direct influence on whether there will be theft or not. Similarly for car value, a direct influence. There are also indirect influences. Socioeconomic status influences car value, home base, and anti-theft, but doesn't directly influence theft. It only influences it mitigated through these 3 other variables. That's really key here. If we want to have a compact representation, we don't want all variables to directly interact with each other. We want to somehow have a sparse set of interactions that captures what we think is enough to capture about the real world. Another example, let's say you want to model a car that just broke down potentially. You want to diagnose that. There are many random variables at play. Battery age, whether the alternator is broken or not, whether the fan belt is broken or not, whether there's any charging happening or not, and so forth. What we see here is we see many random variables, and all of them interact only with a small subset of the other random variables. So we have a very sparse set of interactions, and that's going to be really important to get compact models. Another thing you might be noticing here, and which we'll be doing for a lot of this lecture, even though it's not necessary, often is a quite intuitive way to set up your models, is that they're often built in a causal way. You take a variable, you see which other variables are caused in some sense, in a stochastic way by that variable, and connect things up in that way. So this notation we have here is one where every random variable is going to be a node in a graph. The arcs in the graph are quite similar to CSP constraints. They indicate some direct influence between variables. Formally, they will be encoding conditional independence assumptions. More later about exactly how they do that, but that's formally what they are encoding. If you had the cavity toothache catch domain, this is what the graph would look like. For now, you can imagine that these arrows are direct causation. In general, they're not, but in many examples, they will be, and it's an easy way to get going. Okay, let's try to write out some of these graphs. First one, our n-independent coin flips example. What would the Bayes net graph look like for this example? Just a bunch of nodes, no arcs, because there's no interactions. That's what we have. How about the rain and traffic scenario? 2 random variables. One suggestion is rain pointing to traffic. The rationale would be, well, rain tends to cause whether there is traffic or not. So that's our model. That is, if you want to make more assumptions, you can say they're completely independent. You have a graph like this. If you want a more realistic model with more arcs, which means a more expensive model to work with, you would have rain cause traffic as a very reasonable model for this particular domain. This is a choice though, and it'll depend on what problem you're solving, which model you'd want to work with. Usually though, in this case, you'd want this model over here. Why is model 2 going to allow us to do something more interesting? If you work with model 1, shown here, any inference you do will not allow you to make conclusions about rain by observing traffic or the other way around. Once you make an independence assumption, observing one variable is not telling you anything about the other variable. So you can't really do any interesting inferences in the left model. They're just all independent. Whereas in the right model, you do capture how they relate to each other, and you can do interesting probabilistic inferences. Okay, let's build a bigger traffic model. The variables will be, first one, traffic. So we don't know yet what the other variables are, so just a node for now. It rains. We've looked at that. We know that we like a model where rain points to traffic. Low pressure. Actually, let's make some space here. Low pressure. Well, low pressure is a weather condition that might influence whether it rains or not. So let's put it up here and have it point to rain. Let's not have it point to traffic because it's less likely that low pressure directly influences how traffic is. Roof dripping or not. Let's put that over here. We could think of that as just being influenced by whether it's raining or not. Whether there's a ball game or not. We could put that over here, pointing to traffic. We could also put an additional arrow in here, potentially. That's the kind of thing we have to make up our minds about. We might say that whether there is a lot of rain in this case or not could determine whether the ball game is on or not. Might get canceled with too much rain. Cavity. That one's going to be sitting over here. All right. This is our main running example, alarm network. This is a very common example used in the BaseNet literature. What are our random variables? There could be a burglary or not. Just one variable so far. Let's put it in the middle here. The alarm goes off. There's an assumption here that's an alarm that relates to burglaries. So we'll let that be influenced by burglary. Mary calls. The idea here in this model is that Mary is your neighbor, and she might hear your alarm go off, and then she might decide to give you a call to let you know your alarm is going. You should come check this out. So we'll put an arrow over here from alarm to Mary. Could you argue that maybe your neighbor could have seen the burglar, and if somebody like that was coming through the window next door, they might also give you a call? You could argue that would be true. That's not the assumption we're making in this particular model. This model here assumes that all Mary can do is just hear the alarm, maybe not hear the alarm. John, your other neighbor, behaves just like Mary and will only be able to observe whether your alarm goes off or not. An earthquake. Well, it's possible that an earthquake would trigger your alarm, and then again, John and Mary might just call based on whether the alarm went off or not. Again, you could argue that a reasonable model would be one where John and Mary wouldn't be calling you if there's an earthquake, because they figured out you heard in the news there's an earthquake, and the alarm is just triggered by the earthquake. In this model, that assumption is very different from what you might do. This is the model that's being used in almost all the kind of BaseNet running examples in AI textbooks as the simple example. So alarm is really mitigating here all the influences between the other variables. What are the formal semantics of a BaseNet? We've seen the graphs. We've had some intuition about variables influencing each other. We want local interactions. Formally, a BaseNet consists of a directed acyclic graph. What does that mean, directed acyclic graph? It means that if you follow the direction of the arrows on the edges, you can never travel in a cycle. then for each node, there is a conditional distribution. Let's look at one node over here, particular x. There's a conditional distribution sitting with that node, and that distribution encodes the conditional for x given a1 through an. a1 through an are called the parents of x. They're all the nodes that point into x. You can think of this as describing a causal process, but keep in mind it doesn't have to describe a causal process. The only formal requirement here is that you put a conditional distribution in each node, conditional distribution given its parents, and that your graph is directed acyclic. Together, the graph and these conditional probability tables make up your Bayes net. How do you get probabilities from this Bayes net? Well, if you had a Bayes net over variables x1 through xn, the joint distribution is given by this expression over here. So we take all the conditional distributions that we have sitting in each of the nodes, multiply them together, and that is the joint distribution over all variables. Here's an example. Our toothache cavity catch example again. Here's our Bayes net. 3 random variables. What does the joint distribution look like for this Bayes net? Well, it will be of this format here. So it'll be probability for cavity, which has no parents, so just cavity, times the probability for toothache given its parents, which is just cavity, times the probability for catch given its parents, which is just cavity. By just seeing this Bayes net graph here, we know that the distribution is of this format over here. If you want to compute some specific entry, you just use this equation here with specific entries. What that comes down to is that you would look at all the tables that you have, one for each node, and from each table you would grab that entry, that one entry that is consistent with the instantiation you're interested in. Yes? Okay, that's a good point. So many things in the real world, if you look at your random variables, there will be cyclic dependencies, which are forbidden here in the Bayes net formalism. But they might not be as forbidden as you're worried about, in the sense that when these things happen, usually there is a temporal aspect. And so what you could do is you could introduce multiple random variables for whether somebody has an alarm or system or not. And you could have one for time 0, one for time 1, and so forth. And then the dependencies could run from time slice to time slice. So that's the way you get around those kind of processes where things change over time. And you would think of it as a cyclic process, but really you can roll it out over time. And we'll be looking in one particular lecture on HMMs and dynamic Bayes nets. We'll look at exactly those kind of rolled out Bayes nets that capture these temporal phenomena. You might ask yourself the question, we looked at joint distributions in last lecture, right? And we said a joint distribution needs to satisfy the following property. It's a table with an entry for every possible instantiation of all variables, every possible combination. And there's a number associated with each possible instantiation. And that number has to be positive between 0 and 1, and they have to sum to 1. If those conditions are not met, it's not a joint distribution. Now, what I just told you is that we start with a directed acyclic graph. We assign a conditional distribution to each node given its parents. We just multiply them together, and I told you that's a joint distribution. You should be suspicious because maybe that process doesn't generate a joint distribution. I have not proven to you that this is guaranteed to give you a joint distribution. We don't know that yet. So how can we guarantee that indeed this process works? Let's prove that this works. The starting point is the chain rule. The chain rule says that for any distribution over x1 through xn, you can write it as follows. It's a product of probability for x1 times x2 given x1, x3 given x1, x2, and so forth. What we already have here is one entry for each node in our graph. It might not just be exactly the conditional distribution that we have sitting in our graph. If we make a conditional independence assumption, this one here, for each of the variables, namely that the distribution for xi, given all preceding variables, x1 through xi minus 1, is the same as a conditional for xi given just the parents of xi, then we can make a simplification here. We can go from the original chain rule expression to the expression that we had for Bayes net joint distributions. What this is showing is that the assumption we are making when we build a Bayes net is this assumption over here. In this case, n assumptions. We are assuming that xi is independent of given the parents of xi is independent of all preceding variables in the ordering defined by the Bayes net, except for its parents. All right. So x1 to xi minus 1. Some of these will be the parents of xi. Some of them will not be the parents of xi. The ones that are not have been dropped. So xi is independent of them given its parents. Nowhere in this proof here that indeed we can define joint distributions through Bayes nets, nowhere in this proof did we use any assumption of physical causality. There's no notion of physical causality in the math. Why have we seen a lot of physical causality in everything we've talked about so far? Is because often these kind of conditional independence assumptions are more natural to make if you think in a causal way. If you think how things cause each other, then you'll naturally end up with mitigating effects through the parents of variables and so forth, and it'll just kind of naturally fall out. But conceptually, mathematically, causality is not a part of our definition. Just this thing over here. A node is independent of all its predecessor nodes conditioned on its parents. So once you're given a Bayes net graph, you look at that graph, it directly encodes some independencies. You can look at that graph, you can say, for each node, I can write out this thing over here, which I can also write as xi is independent of x1 through xi minus 1 minus the parents of xi given the parents of xi. That's the type of conditional independence assumption that we are making. Let's take a small break here, and let's look at some example Bayes nets after the break. One good question came up during the break, which is the following. For this all to work out here, there's one assumption that's hidden here and that I want to make more explicit is when you apply the chain rule, you have n factorial different orderings that you can choose from to apply the chain rule. Out of those n factorial different orderings, you need to pick an ordering that's consistent with the ordering of the nodes in the graph that represents your Bayes net. Otherwise, this whole process just doesn't work. So you pick an ordering consistent with the directed acyclic graph that you have for your Bayes net. Once you have that ordering, then you can apply the chain rule consistent with that ordering. You make this assumption over here, which is that xi independent of all the nodes ahead of it, except for its parents, given its parents, and then you get the expression that we had for the joint distribution of a Bayes net. This also shows that this doesn't work if you had cycles in your graph. So the same reasoning doesn't go through if you had any directed cycles, because once you have directed cycles, you will not be able to find an ordering that is consistent with your graph, because there are cycles, so there is no consistent ordering. And so you can't apply this process here to show that if you had all the conditional distributions in your Bayes net, multiply them together, you get a proper joint distribution. In fact, if you had directed cycles in your graph, if you multiply all these conditional distributions together, you will not get a proper joint distribution. This thing doesn't go through. Coin flips. So let's say we have our basenet here, 50-50 for every coin. If we want to compute the joint probability of head, head, tail, head, well, that's just equal to Px1 equals H, Px2 equals H, Px3 equals tail, Px4 equals heads. And we just read out the consistent entries in each of the tables over here. We'd get 0.5 to the power 4. Another example, our rain traffic basenet, and we want to find this particular quantity over here, the probability of plus r negative t. We know how we can build the entire table. We don't need to build the entire table, but building the entire table just means multiplying together all conditional probability tables where you group all consistent entries. So same thing here. This would be P plus R times P minus T given plus R. And you'd grab this entry here, 1/4 times minus T given plus R, which is over here, also 1/4. In general, if you're given the basenet, instead of writing this all out, what you could also do is you could just look at this, plus R minus T. In this table, what's consistent? Plus R. In this table, what's consistent? Plus R minus T. And you'll go through each of the tables, grab the one entry that will be consistent with your full instantiation, and just then multiply them all together. The alarm network. What could the basenet look like for this? This is the graph. The conditional probability tables that are often used look like this. So what's interesting here is look at the basenet. We have a table with 2 rows. So one variable here, so 2 rows, 1 variable here, 2 rows, 2 variables here, makes for 2 to the 2 rows, 4 rows, 2 variables here, 2 to the 2 rows, and then 3 variables here, making for 2 to the 3, which is 8 rows. If we, however, had represented a full joint distribution without using a basenet representation, but just straight up a full joint distribution table, we would have had to represent a table with 2 to the 5 entries. In general, the joint distribution will be a lot larger than the basenet representation. What you also see here is that the parts in your representation that are expensive in the basenet are those variables that have a lot of parents. If a variable has a lot of parents, that will make for a big table associated with that variable. For example, if you had a basenet where one variable had all the other variables as its parent, then you would not save anything by using that basenet, because now all variables would participate in that table for that one node that has everybody else as its parent. So it's important, if you want to get out a compact representation, that your variables in your basenet have a relatively small number of parents. This example we've looked at before, and we've looked at this basenet here. Rain could cause traffic, really meaning that the random variable rain could influence whether there is traffic or not. The natural representation we have worked with so far looks like this. 2 conditional probability tables associated with the basenet graph. And we can build a joint distribution from those tables. For example, the 3/16 plus R plus T comes from plus R plus T over here, plus R plus T in this table here is just plus R. Multiply them together, you get the entry in a joint table. Look at this table. 3/16, 1/16, 6/16, 6/16. We have 3, 1, 6, 6 as our joint distribution entries. I'm going to play a little trick here, or might look like a trick. We're going to reverse causality. And we're going to assume now that we have an arrow from traffic to rain, opposite direction. Arrow has flipped direction from what we had before. Put some numbers here, prior distribution for t, 1 for r given t. Those are distributions we have to come up with now. We build the joint distribution, 3, 1, 6, 6. Same joint distribution. So what just happened here? We have two Bayes nets. They're different Bayes nets because they have a different graph and different tables associated with them. But when you build the joint distribution from either one of them, you get the same joint distribution. So what you see here is that a given joint distribution can often be represented by more than one Bayes net. There's not necessarily a one-to-one mapping between joint distributions and Bayes net. Once you have a Bayes net, it's fixed what joint distribution you'll get out, but for a given joint distribution, there might be more than one Bayes net that can represent it. This is interesting. So why have we always been talking about the arrow from R to T? Why haven't we in the past talked about this model over here? It allows us to do the same kind of inferences. We lose, in terms of an intelligent agent using one Bayes net versus the other Bayes net, it's going to be completely equivalent. There's no difference. They can do the same inferences because they can compute the same joint distribution and then draw the same inferences. The reason it's more natural for us to come up with this one here, the R pointing to T, is because when we look at the tables that we have to build, they're more natural to build. So coming up with a prior for rain is something fairly natural to do. Coming up with a model for traffic given rain is a fairly natural thing to do because that's something you might be able to model. You look at when it's raining, not raining, and see how often there was a lot of traffic, not a lot of traffic. That's a model that's natural to build. You can imagine that's a reasonable model. The other way around is much harder. Building a prior for traffic, just a single variable is usually not that hard. You can still collect data. But then building something for rain given traffic is more difficult because now you're in some sense trying to model how rain is caused by traffic. And this might make your model not as easy to come up with. It can be very tricky to do something right there. So really, it's a matter of what model is easier for you to come up with, and that will drive your decisions. And usually, the causal model will be the one that's easier to come up with. Often, it'll have a small number of parents for each variable if you draw out a causal model, which is good. You have a more compact representation. So that's why we often have causal models. But fundamentally, you don't need to. Also, going back to the definition of a Bayes net, this is really what defines a Bayes net. You have a graph that gives you some ordering over variables. You apply the chain rule, which then you simplify to get rid of some variables that you were conditioning on to get smaller tables. And then you get what your Bayes net definition tells you get as your joint distribution, namely just multiply together all the conditionals at each of the nodes. No causality in here. And the example at the end here also shows that causality doesn't really matter. You could always do things that are not causal and still build a Bayes net. It might just be harder to build in practice. So we just discussed why Bayes nets often have causal patterns, easier to come up with, easier to think about. They don't need to be causal. And sometimes there's not even a way to make them causal. If you had a set of random variables, and your set of random variables were traffic and drips, roof dripping or not, it's not clear which way you would point the arrow. There's no clear-cut decision. Left one to the other to the first one, not clear. But you know there is a relationship between them. They're not independent because they're both very strongly related by whether it's raining or not. Rain is just not showing up here. So by getting rid of the random variable rain, originally we had rain with traffic and drips. By getting rid of the random variable rain, what happens is that now it's not clear how to model this causally. We just have traffic and drips. We could put the arrow this way, or we could put the arrow the other way. Either way we can build a model. Neither one of them is causal, but either one of them could still capture a joint distribution over the two variables that corresponds to statistics we observe in the real world. So that's just a reminder that what these arrows really mean is conditional independence. This is what they mean. They mean this assumption over here. And so for this graph here, no assumption was made actually. No conditional independence assumption was made. For the first variable t, we never make any assumptions. It's the first variable. For the second variable d, we make the assumptions independent of all preceding variables except for its parents given its parents. but there are no such preceding variables. All the preceding variables are its parents, so no assumption is made. In this case, neither of these Bayes nets makes any assumptions about conditional independence. All right, so today was all about representation. How do we go from a lot of random variables to representing a distribution over them without needing to build a joint distribution that is just impractical to represent because it's too large. Not only too large to represent, it might also be really difficult to come up with the numbers to put in that large table. How do you come up with all these numbers? It can be tricky. You might want to talk to an expert, but if your table is really big, you don't have the time to talk to your expert long enough to fill that table. If you try to get those numbers from real-world statistics, if there's a lot of statistics you need to estimate, you'll need a lot more data to get accurate statistics to fill into those tables. So that's what we looked at today. How do you represent a distribution more effectively? The key idea was conditional independence. Next, what we're going to look at is how to answer queries about this distribution. We now have this more compact representation. We already know how to answer all queries about the joint distribution if we had the full joint distribution. But of course, now the tricky thing that we want to do is we want to somehow have the Bayes net never build up the full joint distribution, because that's too expensive to build up. Just keep the Bayes net and somehow directly compute with the Bayes net and be able to answer queries. The types of queries we're going to try to answer are things like conditional independence. Can you, between variables in the Bayes net, infer conditional independencies without building that full joint distribution table? If you have a big Bayes net, can you say, for example, are x5 and x10 conditionally independent given x7? Can you do that by maybe even just looking at the graph? That's for the next lecture. Next lecture, we'll look at more quantitative questions. If you're given this big Bayes net, you're interested in just a query about a small number of variables, maybe a Bayes net over 1,000 variables. Just interested in some query, what's the distribution for x100 given x500 and x100 and x600? Can you somehow tease out the answer to that query without having to first build up the full joint distribution and then bring it down from there? All right, that's it for today. Good luck with your midterms on Monday.